Black hole collision confirms decades-old predictions by Einstein and Hawking. Imagine the force needed to make the fabric of space and time itself shudder. 1 billion years ago, in a distant corner of the cosmos, that exact force was unleashed. Two black holes, each over 30 times the mass of our Sun, ended their cosmic dance in a violent merger. This event sent a ripple, a gravitational wave, racing through the universe at the speed of light. Earlier this year, that ripple finally reached Earth, and a team of scientists, using a machine so precise it can detect distortions 1,000 times smaller than an atomic nucleus, was waiting. They didn't just hear the collision, they heard the clear ringing aftermath. In that echo, they found the confirmation for two of astrophysics' most sacred predictions, proving that Albert Einstein and Stephen Hawking had fundamentally understood the rules of the cosmos. Tuning in to the cosmic symphony. To appreciate this discovery, you must first understand the instrument that made it possible: the Laser Interferometer Gravitational Wave Observatory, LIGO. This isn't a traditional telescope. It can't see light or stars. Instead, its two massive L-shaped detectors in Louisiana and Washington state are designed to listen for the faintest vibrations in reality itself. LIGO works by firing lasers down two perpendicular 4-kilometer-long vacuum tubes. Under normal circumstances, the light waves return and cancel each other out. But a passing gravitational wave will stretch one arm and compress the other by an almost infinitesimal amount. This minute change allows a laser signal to get through. It's the equivalent of detecting a change in distance between our Sun and the nearest star that is the width of a human hair. After first proving its worth by detecting gravitational waves for the first time in 2015, a feat that won a Nobel Prize, LIGO has been upgraded. Its hearing is now sharper than ever, allowing it to detect more nuanced cosmic events with incredible clarity. The event from January, labeled GW250114, was a perfect example. A clearer picture of a dark collision. The signal told a story. Two colossal black holes, spinning slowly in a near-perfect circular orbit, slammed together. The resulting black hole was a behemoth, about 63 solar masses, spinning 100 times per second. But the real magic wasn't in the crash itself, it was in the ring that followed. When the two black holes collided and merged into one, the final black hole was not quiet. It was ringing like a bell that had been struck by a hammer, said astrophysicist Maximiliano Issi, who led the study. This gravitational ringing provided the clearest data ever to test two legendary ideas. Test number 1: Einstein's simple black holes. The first test was of an idea based on Einstein's theory and formalized by mathematician Roy Kerr. It proposes that despite their terrifying complexity, black holes are ironically simple. They can be completely described by just two properties: their mass and their spin. According to the no-hair theorem, they should have no other distinguishing features. The incredible clarity of the GW150114 signal allowed Dr. Issi's team to detect not just the fundamental tone of the black hole's ring, but also a faint overtone, a harmonic that had never been clearly observed before. By measuring these two tones, they could calculate the final black hole's mass and spin with precision. The result? a perfect match to Kerr's solution. The black hole was, as predicted, defined by just those two numbers. Test number 2. Hawking's law of increasing darkness. The second test concerned a law proposed by Stephen Hawking. His black hole area theorem states that the surface area of a black hole's event horizon can never decrease. It can only stay the same or get larger. The team measured the combined area of the two original black holes and then the area of the new single black hole. The math was undeniable. The final area was significantly greater. Hawking's theorem, derived from Einstein's equations half a century ago, was confirmed with stunning certainty. Kip Thorne, a Nobel laureate for his work on LIGO, noted that Stephen Hawking, upon hearing of the first detection in 2015, immediately called to ask if it could test his theorem. If Hawking were alive, Thorne said, he would have reveled in this: the dawn of precision gravitational astronomy. This discovery is a watershed moment. It moves gravitational wave science from the era of discovery into the era of precision measurement. We're no longer just confirming that these collisions happen. We're now using them as sophisticated cosmic laboratories to test the very laws of physics under the most extreme conditions imaginable. As the LIGO detectors and their international partners continue to improve, we will hear more of these events with even greater fidelity. Each one will be an opportunity to ask deeper questions. Could Einstein's theory ever break down? What happens at the very center of a black hole? A ripple in space-time born from an unimaginable collision a billion years ago has today answered some of our deepest questions. The universe has been playing by the rules all along. We are finally learning how to listen closely enough to understand them.